Exponential functions and models. Please know the following definitions and rules for exponents. You've got a product rule, power rule, quotient rule, and negative exponent rule. Remember, if you have a base raised to a power times same base raised to a power, you can simplify by keeping base and adding exponents. So if I did 2 to the third times 2 to the fifth, see what that gives me. I should be able to get it if I do 2 raised to, add your exponents, that would be 8. So bases have got to be the same, you add your exponents. In this power rule, if you'll notice, it's the only one that you really see where you have parentheses, and I usually tell my students that you've got to remember to distribute this exponent through to all exponents inside. Now guys, this is a monomial. This is not true for a binomial. You had to do x plus h quantity squared. This does not work. It only works for monomials. So let's make up a problem here. Let's do 3 raised to the third, and we'll raise that in turn to the fourth. Let's see what we get. Yeehaw. So now if I do 3 raised to, now this rule says I can multiply those exponents. Let's raise it 3 to the 12th and see if we get that same thing. Yes, we do. If you do not see an exponent in the parentheses inside, it's understood to be raised to the first power. Those are the ones you have to be careful. You'll overlook those. So distribute that exponent to all exponents inside, be it either a product or a quotient. My quotient rule, no parentheses. I've got a base raised to a power over same base raised to a power. So if I do 2, say, raised to the third, divide by 2 raised to the fifth. Okay. Let's see what that gives me. 0.25. Well, this tells me I can do 2 raised to, subtract top exponent minus bottom. That will give me a negative 2. There's my 0.25. Now this is nice in that if you do have a base raised to a negative exponent, you've got to know how to make it a positive exponent. This right here, that would be the same thing as 1 divided by 2 squared, which of course is going to be my 0.25. So these are some rules that you've had before in your past. Refamiliarize yourself with those. Alright, let's get on down here. Linear growth and exponential growth. I've got some, very set examples here, but you really need to see the difference with respect to their pictures. We've played with linear equations before. If data increase or decrease by a fixed amount m for each unit increase in x, then it can be written by or can be modeled by a linear function. So I've got points here, and what I did with those points is I plotted them, and you can tell that they're on a straight line. Exponential growth, different ball game. If data increase by a constant factor a for each unit increase in x, that they can be modeled by an exponential function. Now this is the first time that you have ever seen in this class x in the exponent. Okay, now look, I've got, this is an exponential growth data wise. Look at this. It starts off sort of slow, but then all of a sudden it just takes off. Not a straight line, it's a nice little curve. So I've got some examples on the next sheet. We'll go look at that. Exponential function. An exponential function f defined by f of x equals a to the x, where x is a real number. Now the base has got to be positive and it can't equal 1. Has the following properties. The domain, you can use any x value you can think of, but now the range is going to be a little bit different. If my base is positive, there's no way I can raise a positive number up to an exponent and ever come up with a negative value. So my range is always going to be from 0 to infinity. The graph is continuous, no breaks. The x-axis is a horizontal asymptote. So that's what these poor little curves are looking like. I had to do these by hand. They don't look too bad. But anyway, notice this one right here, how it gets close to the x-axis, but it does not cross it. Same thing here. If my base is greater than one, then f is increasing on its domain. So this one right here, when a is greater than 1, notice as I come from left to right, my y values are increasing as I go toward my right. Now, if my base is between 0 and 1, they're fractional, f is decreasing. Notice how it decreases. F is 1 to 1 and therefore has an inverse. We'll get to that later. So again, my base is greater than 1. Their picture will always look like this. So a base of 1.5, 2, 3, 5, anything greater than 1, it will take on this shape. Maybe slow at first, but it'll eventually look like that. If my base is fractional, that is between 0 and 1, it will always be decreasing. So I've got some examples. Let's look at these. And I've got points in waiting. Now, I could get my points by putting it in the calculator, but I think I'd like to try this just a bit. Let me move that over so we can see my calculator here in just a second. These aren't that bad to put them, by hand. If you put -2 in, that's 3 to the -2. Remember, that is 1 over 3 squared, so I get 1/9 from that. If I put in -1, 3 to the -1, this is why you need to know about negative exponents. That would be 3 to the -1, which is 1/3. 0, I love 0. 3 to the 0 gives you 1. 3 to the first is 3, and 3 squareds equal to 9. So let's get rid of that box. Oh, now I've got to put my points in. Let's see, let's put this point 0, 1. I'll put it right there. 1, 3, 1, 3. I think I'm going to run out of room for my 2 9s, so maybe I'll move this down and make this go by my y-axis go by 2's, and it's moving slow. So I'm making my y-axis go by 2's. Okay, so now this one, let me do -1 and 1/3. So -1 is right there, 1/3. Let's see if I can get it pretty close. So I'm estimating the best that I can. Okay. Oh, now -2 and 1/9 is going to be a little bit harder because I'm a whole lot closer. But guys, I don't cross that axis. I wish I could make a smaller dot, but I can't. So I'm not crossing. Nor will any of these other ones. If I had a -3 for x, that would be 1 over 27, even closer. Ugh. Alright, so now I've got 1, 3, so 1, and I'm going by 3. That's right there. Because remember, I'm going by 2's. It's not too bad. Now 2 and 9. So here's 2, there's 2, 4, 6, 8, 9. Now if I could connect this, do you see it'd be coming in and then going up, taking off. And this is resembling this type of picture. That one right there. Let's see if I can connect it. I'm going to try. Let me try squiggle. So it's coming in here. Oopsie. And then it's just taken off. Well, I can do better if I had pencil and paper. But it's still, as best as I can, resemble that little fella right there. Okay, let's try this one. So this can be seen in two different ways. Now 2 to the negative x is the same thing as, if I move that to the denominator, that would be 1 over 2 to the x. Okay, but 1 raised to anything is going to give me 1. So I could see it either one of these ways. So you might try it via your calculator. Let me clear this thing out. Oh, I was going to show you how to get points. What do y equal? And you should already know this. 3 raised to the x. Let me go to my table. So there's negative 2, which is that 1/9 is point bunches of 1s. There's negative 1 1/3. Look at this. X equals 4 and it's 81. I try to stay real close around 0 because I don't want to graph that one. I don't know about you. So let's go back to y equals. Let me clear this off. Let me do 2 raised to the negative x. And also I'm going to do 1 divided by 2 raised to the x, because I want to see if they are the same thing. Let me go to my table. Look at that. See, they're the exact same thing. So if I put negative 2 in, if I put it in here, that would be just 2 squared, so I would get 4. That's where they're getting 4. If I put negative 1 in, well guys, if I put negative 1 in here and use my rules, that would be 1 to the negative 1, 2 to the negative 1. I have to get the reciprocal, so that would be 2. So, you know, there's a couple of ways you can find these problems, and since I see all the points on that side, I'm just going to go ahead and delete that. If I put in 1, well, 2 to the negative 1 is the same thing as 1/2 raised to the first. There's my 1/2. So I think I'll do these by ones because I think my picture is big enough here. So x is 2, y is negative 4. Okay. Negative 1, 2. Let me move it over. I'll nudge it a little bit. 0, 1. Not too bad. 1 1/2. And now this one I go to x is 2 and I go to a 4th. Now remember, the x-axis is my horizontal asymptote. So this thing is going to snuggle as it comes down through here. Alright, let me go and see if I can do my little squiggle here. So I'm coming in this way. Ugh. I'm hitting. Oh, this is horrible. Ah! Yuck. I don't like that. You plot your points and you make your picture. And I know it'll be a whole lot better than mine. Let me ask for the graph. Oh, my window's really messed up. Let me do zoom 6 to recenter. Well, Pooh Bear. Zoom 6. Yeah. And it would take on that shape that I've got here. Zoom 4 would get me a little bit closer and be a little bit prettier. Yeah. See how it's snuggling? But guys, it's not going to cross. Won't cross. Now it says the closer the base is to 1, the flatter the graph. I'm almost done. Just stay with me just a little bit more. Let me clear this off. Let me put in, say, 1.25. Now that is greater than 1, so it should take on this shape right here. Let me raise it to the x power. Let me do a zoom 6. See how flat it is, but it does eventually take on that form. Now I want to show you one more thing why the base can't be 1. If I do 1 raised to the x, it does not take on this family characteristic of starting low and finishing high, or starting high and finishing low. So it's just not allowed. So that's it for this one. Thank you.